Okay, there we go. Check my distance here. So in this series of videos, what we're going to be looking at is objects that are not moving in a straight line. Okay, they could be changing direction. Now, they might be changing direction in a circular path, like the example we have here, or they could be doing something different. All right. Now, when an object is speeding up or slowing down, it accelerates. We know that. But remember, if the object changes direction, it also is accelerating. Okay. So you can change speed, but not direction. You could change direction, but not speed, or you could do both. Okay. Now, in the case where you're doing both, what we have to do is we've got to realize that when we talk about the acceleration of the object, it's really going to be some what we call tangential acceleration plus some normal acceleration. Okay. So tangential and normal. All right. So let's look at our drawing here. So our boat, there's a tangent line to that. Okay. Now, the velocity vector corresponding to the motion of the boat is always going to be tangential to the trajectory, to the circular path. Okay. So velocity is always tangent to the trajectory. Okay. But then if we talk about our acceleration, we could have an acceleration component this way that's also tangential. Okay. Now that tangential part is responsible for the object speeding up or slowing down. So think about the tangential acceleration like the movement of the odometer. Okay. So, you're going up or maybe you're coming down. Okay. That's what tangential does for us. Our normal acceleration is in this direction towards the center. So there's A sub n. Okay. Now, back in physics, we usually call this centripetal acceleration. Okay. And that's okay to call it that here too. Calling it a normal acceleration is a little more generic, it's a little broader type of idea, but it's the centripetal acceleration. Okay. So the relationship between, I got to get a new color, guys. Here we go. The relationship between the velocity and the tangential acceleration is the same that we've seen already. Okay. In other words, Bumblebee, Sam, Optimus Prime, A is equal to V dV ds. All of those things are in play. Okay. All of our derivatives, all of our usual relationships. Okay. For A sub n, okay, what we're going to use is we're going to say A sub n is the speed squared divided by the radius of curvature. Okay. Now in physics we used an r for that. We said v squared over r. Here in this book they use rho to correspond to the radius of curvature. All right. They do that because generally r corresponds to a location vector, a position vector. All right. So they're trying to avoid confusion that way. Okay. So let me undo that. I think everybody's got an idea there. Let's see. We'll try that color. Okay. So let's go ahead and get the tangential acceleration. That's the easiest one. Let's get the low-hanging fruit. Okay. And since we know that v is 0.0625 t squared, at is just the derivative of that thing. Okay. dv dt. Okay. Which makes it to be 0.125 times t. Okay. Now we could go ahead and plug in here for our time component. Okay. So we want to know how fast is it going at, or what's its tangential at 10. So then that becomes 1.25. Just like this. Let's go and get our velocity as well. V at 10. Okay, that turns out to be 6.25. That one's meters per second. This one is meters per second. squared. Okay. So now that we've got those, let's dig in and get the normal acceleration. Okay, so that's the v squared over rho term. All right, so v squared over rho. And we want to use this speed right here because we're interested in what's happening at the 10-second mark. So at 10 seconds, it's going 6.25. So that means here we're going to have 6.25 meters per second squared over rho, which in this case is 40 meters. Okay, so let's watch what happens with our units. Okay, so I'm going to have meters squared over seconds squared dividing out a meter. So I'm going to be left with meters per second squared. Okay, so everything checks out there. Now, once you do that math on that, turns out your normal acceleration is pretty small, 0.977 meters per second squared. Okay, there we go. All right, so all that remains then, okay, in order to get the magnitude of the acceleration is you're going to plug this in up here, plug that one in over there, and get your answer out of that. Okay, pretty easy. Now, sometimes in this section, your book says determine the magnitude of its acceleration. Okay, just like this one does. Sometimes it just says just find the acceleration or find the value of the acceleration. Okay, but what you need to know is that in this instance, okay, if we've got a tangential, if we've got a normal, we're going to need both those. We'll combine them with Pythagorean's theorem. Okay, there we go. All right, now the next couple of well, I'm going to do two different examples in the next video. Okay, so this will be a little bit long, but most of these are just as simple as you've seen right here. Okay, find AT, find AN, put them together. Okay, they're sometimes finding those things. They might take. You might have to take the scenic route, so to speak. Might not necessarily be so straightforward, but again, the basic idea is going to be the same thing. Find the tangential acceleration, find the normal acceleration, and combine them. Okay? So we'll get to that in the next video.